Hello and welcome back. We're continuing our progression now through Chapter 17. Subject is sound. And we're going to begin discussing the Doppler effect. So you have experienced the Doppler effect when you're standing, for example, on Central Avenue in the heart of Nob Hill, and you hear a siren coming toward you. Think of it as an ambulance moving toward you. And as it's coming toward you, the sound is getting louder and louder and louder and louder and louder. And then once it passes you and starts moving away, the sound seems to diminish. And it has something more to do than with the fact that the distance is smallest when it's in front of you and furthest away when it is on approach and on exit. It has to do with the fact of the sound wave's frequency impacting your eardrums. As the ambulance is moving toward you, each time it emits a crest, it moves a little bit closer before the next crest is emitted. And so the frequency at which those crests are impacting your eardrum is at a higher rate than if that ambulance was sitting still. When the ambulance is moving away from you, it emits a crest and then moves a little bit further away before it emits the next crest. And as a result, the frequency at which those sound waves hit your ear is at a smaller frequency than you would hear it if you were at rest with respect to that ambulance. So this is the Doppler shift. The frequency at which a wave impacts your ear is dependent on the rate of change of the distance between your ear and the source of the wave. If their distance is changing as a function of time, then we are going to hear a different frequency than the true frequency of the sound. So let's make some definitions here so we can understand these formulas that have to do with calculating the frequency that you would hear when a source is moving relative to you or you're moving relative to the source. So V sub W is going to be the wave speed. That's going to be how fast the wave travels in the medium it's in. So for the example we were just talking about, this would be the speed of the wave in air. V sub S is the source speed. So this is how fast the entity that is creating the sound is traveling. So this would, for example, for the problem that we were just talking about, the ambulance's speed itself. V sub OBS is the observer's speed. Note there would also be a shift if the ambulance remained stationary and I went running toward the ambulance or running away from the ambulance. In both those cases, the rate of change of distance would be changing, right? We would get a rate of change of distance, and so there would be a Doppler shift from that as well. So in this top equation right here, what we have is a stationary observer and a moving source. So this is the example we were just talking about, where we are standing still on Central and there is an ambulance that is moving relative to us. That ambulance is moving at a speed V sub S, and it's emitting a sound wave, and that sound wave is traveling at V sub W. The frequency we would hear as we stand there on Central is going to be equal to the frequency, the true frequency of the wave. This is going to be the frequency that the driver of the ambulance would be hearing for the siren, times the speed of the wave in air, divided by the speed of the wave in air, either plus or minus the speed of the ambulance or the source that is creating the sound wave. You're going to use plus here. Notice that when you do use plus, this denominator is going to get larger. If the denominator gets larger, then this frequency is going to go down. So that's got to correspond to the ambulance moving away. So the plus sign is going to be used for moving away from the observer. The minus sign is going to give us a smaller value in this denominator. That's going to yield a larger frequency that we observe. So that's going to correspond to the source moving toward the observer. So this is the formula that we use when we have a stationary observer and a moving source. But as I just said earlier, we could also have the observer in motion and the source is stationary. And that's what the second formula is for. It's a stationary source and a moving observer. So the frequency the observer is going to hear is equal to the true frequency that is emitted by the source times the speed of the wave itself plus or minus the speed of the observer divided by the speed of the wave. Notice that in the numerator here, if I use a plus sign, that's going to yield a larger frequency for the observer than the true frequency. So that's got to be closing the distance between the observer and the source. So the plus sign is going to correspond to the observer moving toward the source. So the plus sign is used for toward the source. The minus sign is going to create a smaller value for the frequency of the observer detects relative to the true frequency of the source. So the minus sign then is used for the observer moving away from the source, expanding the distance between it and the source. So these two formulas allow us to calculate different scenarios and give the frequencies that are detected in those cases. Somewhere, someplace, sometime, maybe in mainstream lingo or somewhere in your high school physics classes, you learned about the universal redshift, or you've heard about the universal redshift. This also has to do with the Doppler effect. So it turns out that when we look at other universal bodies out in space, other stars, planets, those kinds of things, what we see is that the frequencies we are detecting from them are all shifted to be slightly lower than they really truly should be. So if we're detecting smaller frequencies than the true frequency that's being emitted, that tells us the distance between us and them are increasing. We don't know if it's us moving backward or if it is the entity that is emitting that frequency moving forward, or both. But the distance between us is expanding as a function of time. And so the redshift is the name given to that. And why red? Because in the light part of the electromagnetic spectrum, that's the part of the electromagnetic spectrum that these detectors can actually see. Red is the smallest frequency amongst those colors. Red is the lowest frequency, and blue is the highest frequency. So we refer to that as a red shift. So this gives us an idea of the Doppler effect, how to use these formulas, and we will continue moving through Chapter 17 next time. Thank you.